Good evening and welcome back to AP Stats Notes Online. Still talking about modeling distributions of data and positioning within a distribution and things like that. So we've talked about percentiles and z-scores. They both describe location in a distribution, but they do it in different ways and using different calculations, right? So all throughout this, trying to figure out how to handle our data once we get it, we've established some sort of step-by-step process or a guideline here that what we do. So we're going to grab our data and we start applying some of the tools that we've learned in one, displaying the data first. We want to show some graphical representation of the data so we get an overall picture of what's going on. And then we calculate some numerical summaries, some calculations on our data, so we get some more specific information from the information that we've gathered. We can add one more step in this analyzing process if it seems to make enough sense. So when we collect our data and we're starting to explore it, we want to know what we're being told from our data, then we want to go through this process, right? Like I said, you're going to make a graph, and in that graph, you're looking for an overall pattern, shape, center, and spread. Are there any outliers, unusual points, any striking departures from this pattern? Then, like I said, we're going to calculate a numerical summary so that we can a little bit more specifically describe the center and spread of our data. Sometimes when we graph our data, the overall pattern is so regular that it makes enough sense to lose some of the picture and just describe it by a smooth curve. It's usually with a large number of observations. That's usually when this starts to make enough sense. But we can sort of sketch out a smooth curve. And that smooth curve is called a density curve. So some rules about a density curve. So a density curve is simply a curve that has to meet these two criteria. And 1, the curve is always on or above the horizontal axis. Now, I've already drawn some density curves for you in Chapter 1 notes, and I'm going to reference those in just a minute. And if you don't have those with you, that's okay. You'll probably remember us doing it, and you can always go back and look at it later. But they're always on or above the x-axis because the idea is we're trying to just show sort of the top of our distribution, whether it's a dot plot or a stem plot or a histogram. The curve is supposed to just give us an idea of the tops of those distributions. And all of those distributions, our data lines up above the horizontal axis. So it makes sense the density curve has to be above the horizontal axis. The area under the curve, so it's like a curve is an umbrella, right? And the idea behind the curve is that it should cover all of our data. So the area under that curve should represent 100% of our data. Everything should be under that curve. And so if we were to try to section off this curve and calculate the area, then the total area should be exactly 1 or 1%, or sorry, 1 to represent 100%. That's 100% in decimal form, right? So a density curve describes the overall pattern of a distribution. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. Now, what does that mean? I'll give you an idea, and again, I'm going to reference back to the chapter, section 1.2.1.3 notes, and kind of tell you what this is getting at here. Okay, so let me show you this real quick. And again, if you don't have these with you, that's okay. You can always go back and reference these at some other point, right? So if we go back to this, the pulse rates, and the fact that we created a histogram for it, then there aren't enough observations. This is, and I can't remember, it's either second period or seventh period, one of the bigger classes, but 23 observations are not nearly enough to kind of get us into a situation where it makes enough sense to create a density curve. But I'm going to try it anyway, so just sort of bear with me here. If I can ever get my pen to pop up and start working. Okay, it's not going to want to, so bear with me just for a second. Here we go. Do. Okay, there we go. There's a big bar in the way there. So, all right, so we have this curve, and a density curve is just sort of a quick sketch of the tops of these boxes. So it would look something like that, which is a weird density curve. All right, and again, not enough observations. This is just to kind of get you an idea. So that might be the density curve for this histogram, and so 100% of the observations are under this curve, right? 100% of the individuals are under here. The curve is above the x-axis. Now, if I wanted to know the percent of individuals that are in a particular area of this distribution, say here or here, then I would be calculating just the area under this curve. Okay, and so that would tell you the percent of all of those observations that fall in that interval. Now, a histogram does it too, but the density curve is a little bit more of just a quick estimate. Okay, so maybe we'd look at this without the histogram in it. And if you reference back to the first page where I started talking to you about shape, these were all density curves. Okay, we didn't know that at the time, but these are all density curves. Symmetric, skewed right, skewed left, and so density curves still show you the same thing that we were talking about before. So again, under this density curve, it's all above the horizontal axis. 100% of the observations are under here, right? So if I wanted to know what percent of observations are in this are here, then I would just calculate the area for that guy right there, okay? Now, that can be kind of tricky. This curve is going to have, it's not going to be straight lines, right? Any area formulas that you might be thinking about right now, rectangles, squares, triangles, p-grams, rhombus, trapezoids, things like that, they need straight sides, right? Those are all quadrilaterals. Quadrilaterals have segments for sides, right? Going back to geometry. Really, symmetric, skewed right, skewed left, unimodal, bimodal, these are all going to have curves. And any of you guys that have taken calculus or took calculus last year might start to think, you know what, I can find the area under the curve if we just differentiate. And that's true. But that's more math than what we want to get into. The only density curve that makes sense to just directly take the area under is a uniform curve. A uniform curve is going to be maybe straight across, right? Because if you imagine a histogram, all the bars being the same height, that's what a uniform curve, uniform distribution is. So if I wanted to find the area under this curve, then of this interval, then I've got a rectangle. And it just becomes length times width. That's how do you find the area of a rectangle. So where Your width might be how tall, your count or your percents of the tops of these boxes, and then your width, or your length becomes just the interval values. Okay, so if this were, this x-axis was scaled, so this was 5, this was 10, and we had all of our histogram bars were exactly, 10, if these were counts, 10 high, then our percent of observations, okay, would be length times width. And this would make more sense probably if this was in percents, but hopefully you're getting the picture here. So maybe this is 10% here. So you go 5 times 10%, and so 50% of the observations would be in this interval right here. Anyway, it's a rectangle, so you just go find the area of that rectangle. But all these other guys had these curves in them, and so they're a little less regular shapes. But that's a density curve, and that's the idea behind a density curve. Okay, so go back to our definition here. So a density curve is always on or above the horizontal axis. The entire area under the density curve is 1 or 100%. A density curve describes the overall pattern, the area under the curve, and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval, right? And so maybe a better idea here is to take a look at this histogram, which shows the ITBS vocabulary scores, which is from a 7th grade class in Gary, Indiana. ITBS is the Iowa Test of Basic Skills. This is the histogram, and 947 is quite a few individuals, and so we could kind of fit a density curve the best we can, right? I mean, it's not going to be perfect. You're going to have spaces here. And again, for any of you calculus people, that was the idea behind differentiating, is that you could try to find the area of the curve by creating a bunch of rectangles that fill up all the space, but you always have this, this excess above the curve and this shortfall under the curve. And so differentiating kind of gets you to a point where you can find the area exactly. Now, again, we're not going to do that. That's more math than what we want to do, but that's the idea of a density curve. It just kind of gives you an overall pattern. So what you could imagine is pulling all of these bars out and just leaving the red curve behind, and that would be your density curve. Okay, and so the proportion of individuals. Really? Okay, so if you wanted to find, I did it again. Ugh. The proportion of individuals that were in this interval, then you would just find the area under that curve. All right? All right. Anyway, moving on. Density curves still have measures of center and spread. They actually still have shape. So we'll still use the same idea for measures of center and spread for density curves. Okay? One thing I do want to go back to really fast is, so first of all, obviously, no distribution is going to perfectly fit underneath the density curve. You can see that from the histogram here. What we're looking for is for the curve to be accurate enough that we can use it for practical purposes. We're going to use certain density curves to calculate some things, and the uniform curve is the easiest way to do some calculations, find some proportion of individuals that fall in certain places. So a uniform curve becomes pretty nice. The most common, or at least the most well-known density curve is the normal curve, right? Is the normal curve. The normal curve is your bell curve, right? You always hear teachers talk about the bell curve. That's your normal curve. And we'll discuss that some more in section 2.2 and how to use the normal curve, okay? So anyway, there are a bunch of different types. The normal curve is the most well-known. And the uniform curve is the easiest to do calculations on, okay? So we're going to use measures of center and spread because they apply to density curves as well. So measures of center, right? We've got median and we've got mean. Density curves can take on the same shape as any other distribution. They can be skewed left, skewed right. They can be symmetric. They can be uniform. They can be bimodal. They can be all these things that first page of your section 1.2.1.3 notes describes. Okay? Well, median and mean and where they are in relationship to each other follow the same rules for density curves as they did for any other distribution. So to get an idea, if all you're looking at is a density curve and you want to start trying to figure out where the median and the mean are, then there are a couple of sort of ideas that you can use here. The first one is that the median of a density curve is what can be called the equal areas point, right? There's the same amount of area to the left as there is to the right. Because again, area under that curve represents percent of individuals. So the median needs to be that point where the area under the curve to the left is the exact same as the area under the curve to the right. And so another way to look at this, and I swear if I keep doing this, is that it divides the area of the curve in half. Okay? The mean, if you're looking for the mean, it's a little bit different, right? For the mean, we want the weight of our individuals to be the same on both sides. And so it becomes a balancing point. If I were to take that density curve and make it out of metal or wood, then the mean would be that place where I can put that density curve on the tip of a pencil and it would be perfectly balanced. Okay? The median and the mean, if it's a symmetric density curve, just like a symmetric distribution, the mean and the median should be the same. The percent should be cut in half at the same place where you would perfectly balance that curve. Now, if we're talking about a skewed density curve, then again, the skewness is going to really pull that mean to one side or the other. It's going to pull it towards the tail, right? So here's what we're talking about. In a symmetric, and this right here is a perfect idea of a normal curve. So it's symmetric, and so your mean and your median should be right in the same place. If you get into a situation where your curve is skewed right, then that tail is going to pull the median more. Now, it probably will affect the median some, right? The median is not going to be at this peak anymore. It's not the mode. The median and the mode are not the same thing necessarily. So the median will come out some, but it won't come out nearly as much as the mean, and we know that already. We've talked about that a lot already. So if you're trying to figure out where the median and the mean are in a density curve with nothing else to go off of, that's a pretty good indicator there, okay? Now, the last thing I'll tell you is measures of center and spread we'll use for density curves so that you get used to the notation. We've been using X bar and S sub X for our mean and our standard deviation, and of course M for our median. That's because we're dealing with sample data, and we're dealing with actual values that we can go find the mean and the mean and the standard deviation with. What you'll see used for density curves a lot are mu and sigma for center and, well, not even center, more specifically than just center. We use it for mean and standard deviation. Okay? And that's because we're dealing with sort of some approximates. Mu and sigma we generally leave for population mean and population standard deviation. but those are usually going to be estimates. We're not going to normally know the actual population mean and population standard deviation. So just so you understand that when you see mu and sigma, that's what that dude with the tail is right here. It's Greek letter sigma. Those are the center, the mean, and the standard deviation for a density curve. Okay? So that's all about density curves. And you'll be asked to try to find the area under some density curves. Again, the uniform curves are going to be the easiest ones to do that for. And then trying to figure out where the mean and the median are going to be the most important parts here. Okay? That's enough about density curves right now. Like I said, in the next section, we'll talk about the normal curve and a lot of the things that we want to do with it. There's a check thing on page 103. Check that out. Make sure that you understand those. We'll take a look at them in class on Monday. And then starting Monday night, we'll start going through a normal curve and the normal distribution and a lot of the calculations that we can do with that. Okay? Probably looking at a quiz on Tuesday. So be ready for that. All right? Homework's in your text. Enjoy your homecoming weekend. See you guys on